So, this week, I mentioned this at the end of my Mass Effect stream, but for those of you who missed that or were doing something else, whatever, it's fine. I was going through kind of like, I have my textbook, hey, Christoph, that I've usually taught out of. And that's kind of where I'm pulling all of these from. I'm making these lectures every single week, from scratch, but following this pattern of this textbook. But this textbook is about 7 or 8 years old. Dracorex, hi! And so it goes right from our solar system exploration, which I think was structured pretty well with the terrestrial planets, the gas giants, the Jovian moons, and then the asteroid belt, the Kuiper belt, comets, and dwarf planets, and all of that. I think that structure was pretty good. But then the next chapter right after that goes into exoplanets, and it's just a really brief discussion of like the methods for detecting star systems, planets around other stars. And that's it. And since that was written, we've detected a lot more star systems that I want to spend a lot more dedicated time talking about, particularly things like the TRAPPIST system, which a lot of, you've maybe heard about. But details like that, like TRAPPIST, Kepler-22b, these ones that are a little bit more notable, they have some differences in the fact of like their parent stars are slightly different than our star. And so I didn't want to jump in and start discussing those star systems without going through star classification first. So we're going to do that. So we're skipping the exoplanet thing, which I advertised last week, so I'm sorry about that. But we're going to skip the exoplanet for now. We're going to talk about our sun this week. Hey, Shortman. And then we're going to go from talking about our sun into stellar classification and particularly the HR diagram, how we classify stars, how we can view them. Then we're going to be going into the solar life cycles, and then that should take us into exoplanets. And honestly, that is kind of Astronomy 101. Once we finish with that, we've done all of Astronomy 101. So I'm still deciding what we want to do after that. Maybe we'll take a little hiatus over the holidays, come back, but it's only going to be about 3 or 4 maybe more classes. And then maybe we'll get into Astronomy 102. So, anywho, so that's sort of the context for why, if you were here last week, we were talking about that we would discuss exoplanets this time. And then as I was looking at the material, I decided to skip that, do this stuff next, and then we will come back to that later. And so let me just pull these things up real quick. So last week we talked about our favorite dwarf planet, Pluto, dwarf planets in general, and why Pluto is a dwarf planet, and it's okay, it's still cool. And then we talked a little bit about cosmic collisions. So, because we were talking about the context of asteroids and the Kuiper belt and how, big or small the distribution of material is in there, we talked about what happens if stuff is going to crash into the Earth. But this week we're going to be talking about the sun. And so the big key is that if you think about it, ancient astronomy, we did that right at the beginning of this course. We talked about how the ancient astronomers viewed the night sky, how they problem solved this idea of the celestial sphere that moved around above us, trying to figure out why things looked the way that they did. But the question of why the sun shone is a pretty interesting one to think about. And it's really fairly recently that we actually figured that out. Now, logically stating, these ancient cultures, what they understood was that the sun rises every single day. And the sun rises every single day, and then it sets. And when it does, it warms up. If it's covered, it's cooler. So those logical statements said that, there might be some type of fire, some source of fire. Maybe someone turned on the light. But as we got it, but there really wasn't like any more understanding than that. Now, the ancient cultures had no context for like how far away the sun was, so that made it a little bit harder. And also, I have to, M. Chupin, I do like that. I mean, that's some dedication to Pluto right there. But you'd have to also strip it of its companions. So if you want to live with the consequences of that, I wish you luck. I jest. But yeah, so these ancient cultures, right, when they're thinking about the sun, they have no context for how far away or how big the sun is. They know that this big orb rises every day, sets every night, warms up the sky, and it cools off when it goes away. So they thought that it might be some type of fire. Now, in the 19th century, by the time we got to that, we had a better understanding of the size and the distance from us. You know, we're starting to measure the other objects that we're seeing. We've got telescopes that we're using regularly. And we're starting to realize, okay, like this sun is this big and it's this far away. That ruled out fire in the traditional sense for being a source of that, whether it's wood, oil, coal, whatever it could be. People were like, okay, if it's that big and that far away and giving us this much heat, there's no physical way you could just burn a candle that hot and get that amount of energy off of it. So that's where they kind of ruled it off. And they were like, okay, well, something else is going on. We don't have the science for that right now. We can't really duplicate this in a lab, you know, at this stage. This is the 19th century. So good luck. One of the things that they did start thinking about was this idea of plasma, right? Maybe it is a superheated gas, which is a good guess, but thinking about how it continues to shine and how it continues to give off heat, their main proposal was something called gravitational attraction. Or contraction, sorry. Gravitational contraction, just in the sense that you have this big ball of hot gas, and as it collapses on itself, as it's collapsing, it's getting more dense. It's getting more dense. The temperature is going to increase because you have this friction. It's getting closer together, and it's giving off that heat. And that wasn't unreasonable. Just doing the calculations for how big it was and the contraction and how much heat was being given off, that did kind of answer it, but it would have aged the sun to be only about 25 million years old. That process would eventually, you know, if it's just constantly contracting and giving off heat, and as it loses heat, it contracts more, which generates more heat, gives it off, loses it, keeps contracting down. It's only going to be aged to about 25 million years. And concurrently, scientifically, we're discovering that, well, that's much younger than we're able to date rocks now. Carbon dating was becoming a thing. We were realizing rocks on the Earth were much older than 25 million years. So that didn't quite work, but we were kind of onto the right thing there. The big breakthrough happened in it was in 1905, when Einstein published the paper on energy mass equivalence, this idea of E equals mc squared. And really what it comes down to, it's not just saying E equals mc squared, but the origin of it is really talking about the chemical processes and how much potential, if you remember this from our sort of quick physics background that we did, within atoms is stored potential energy, the energy that's keeping these atoms together. If you were to release that is this equation, E equals mc squared. And so once he was starting to realize how much energy is stored in atoms themselves, that's when this started to reframe the way people were thinking about how our sun shines and the way that it shines. And the answer to that is nuclear fusion. The big key with it is like, okay, so how did this start? And we talked a little bit about the formation of the solar system, so this should not be completely unfamiliar for people. But it really is this idea that it is a, yes, there you go, a gigantic nuclear furnace. It's sort of, well, it's a fusion furnace. So here we have fusion versus fission. Now, fusion is when you take atoms and you bind them together, and we'll go into the process of how the sun does that. Fission is where you split them apart and release the energy, and that's more traditional of what we do here. And yes, Cairo, exactly. Finding out that mass and energy are convertible and the same in some way is a huge deal. And obviously, if you follow my stuff, you've heard me talk about that a lot when it comes to how you can warp space-time if you don't have mass. But when we talked about the formation of the solar system, this idea that we had this big cloud of dust and gas that started to condense, this gravitational contraction that's happening, But as that's happening, it is heating up. It's giving off heat, but it's getting super, super dense. And as it's getting more and more dense, it's heating up, but then it reaches this point where it's so hot and so dense that it does start to fuse together. And then it reaches this thing called gravitational equilibrium. And I'll go into a little bit about what that is as well. I didn't pull a picture of this, but essentially what it is, and I'll be going into the overall structure of our sun. But essentially what's going on is this idea that it is falling in on itself. It is a massive, heavy ball of gas that is collapsing in on itself. But as this fusion process is happening inside the sun, it's giving off light, and that's what we call radiation pressure. And that radiation pressure is holding the sun up against the gravitational collapse. So that collapse that they were calculating that would heat, that would give off enough heat for the sun, but only last for 25 million years, lasts much longer because of this radiation pressure from the fusion that's happening in the core is holding the sun up against itself. And that's what we call, it's either referred to as hydrostatic or gravitational equilibrium. The book I have uses this kind of dorky, but good analogy of like thinking about acrobatics and gymnastics when you have stacks of people lying on top of each other and holding each other up. As they layer on top of each other, they're going to get heavier and heavier, and the person on the bottom has to use more pressure to hold the whole thing up. That's kind of a decent analogy for this as well. But let's look into the overall structure of the sun. There's multiple zones here. The sun's got some weird stuff to it. It's a quirky little thing, and I'm just going to step us through each kind of component on this diagram. Now, we can go out, in, or in, out, but I think starting in the core is an okay way to go. And then we'll get into, once we finish going through this whole area of the sun, what we'll do is we'll go back to the core and actually talk about the nuclear fusion process itself. But that nuclear fusion process, that's what's happening here in the core. That's hydrogen being fused into helium, which again, I'll get into the details of next. And then this radiative zone is beyond which it's dense enough that it can be fusing, but it's still just, that energy is just being radiated out. So it's just traveling straight out. And that's what we call the radiative zone. So we talk about, it's a fairly calm plasma area. The temperature is about 10 million Kelvin. And in order to have nuclear fusion, you're looking at more about 15 million Kelvin. And the density in the core is more than 100 times that of water. The pressure is 200 billion times that on the surface of the Earth. And then I have some more fun facts about that when we get to it. But yeah, then we have the radiation zone. And this radiation zone is where the energy is just moving outward purely in the form of radiation, photons of light. Temperature is about 10 million K, and very hot, giving off a lot of energy in the X-ray there. And then outside of the radiative zone, we get actually this area called the convection zone. Now, if you have a convection oven, this may sound familiar, but what it is where this cycle of you have heat on the lower layer and that starts to rise. And as it rises, it cools off. And so it falls back down. So you get this convective layer where there's this constant rise and fall of plasma due to just temperature variations that are happening. As it's getting out, it's getting a lot less dense. So you're able to have this convection zone occur. And that's just where we're seeing a lot of that turbulence come in. And it purely has to do with the fact that the density is now low enough that it's not all being compacted and held together, and all that the photons are just trying to make their way out. It gets to the point where it's less dense such that you can get this circulation in there. And that's what we call this convective zone. Now, outside of the convection zone, we have what's called the photosphere. Now, so let me see. The photosphere is really the visible surface of the sun. So this is the part that we're actually able to see visibly in the visible part of the spectrum. Not looking directly at it, but using a filter. But what's radiating in the visible part of the spectrum. If you remember when we talked about spectroscopy, and yeah, there you go. When we were talking about spectroscopy, we were saying how the sun peaks at a certain point based on how hot it is, what the temperature is. That peak is where we were talking about the photosphere. So that's where that part is. It's actually far less dense than Earth's atmosphere, and the temperature of the photosphere is just under 6,000 Kelvin. This is where the surface is kind of churning and boiling, if you've seen those cool videos and stuff of the surface of the sun in the optical range with filters. Don't look directly at the sun. So we have about 6,000 Kelvin when we're at the photosphere. And then we get to the chromosphere. Now, the chromosphere is sort of that middle layer of the atmosphere. And now we're talking about it being about 10,000 Kelvin. So it was about 6,000 at the photosphere. Now it's heating up. It's getting to about 6,000 here. Did that twice. 6,000 in the photosphere, 10,000 in the chromosphere. So it's getting hotter. And this is mostly giving off X-ray and ultraviolet light. So this is the bit where if you see those cool, quirky videos of the sun, and I've got some pictures of it later. And in fact, what you're seeing right here, this is a lot of that as well, this chromosphere area. And then the weird thing is we get into the corona, and that's really, the outermost layer of the atmosphere of the sun. The weird thing is that we went from the photosphere being about 6,000 Kelvin to heating up to the chromosphere, which is about 10,000. And then the corona is almost 1,000,000 Kelvin. 1,000,000 Kelvin. So incredibly hot. And Domestic asked, why does it get hotter the further away? And you know what? The answer to that is still, we don't know. It's really a puzzle. There's lots of research, but this is one of the primary focuses of solar physics research, is trying to figure out why that's happening. Now, again, as a couple people are noting here, the density of the photosphere is really low. It's so low. The fact that we can see it is very bizarre. And then this temperature gradient getting hotter as you're getting outer in the atmosphere doesn't make a ton of sense. Now, there are some good theories for this, which has to do with different types of, at the quantum level, the radiation, the interaction between particles, how they're able to heat each other up. And there's various models that try to explain this, but it is still a major question. So we're still launching solar telescopes. We've got a new one there, reached there recently. It is to study exactly this, to try to understand why it's getting so much hotter in the corona. Like the photosphere, the chromosphere is still kind of weird, where you're going 6,000 Kelvin to about 10,000 Kelvin. But then to jump from 10,000 to 1,000,000 is bonkers. And that's still definitely something that we still want to understand. Then once we get out of there, then we're really talking about solar wind is a little bit beyond that corona. That's the radiation particles that leave the sun and travel out through the solar system. And then sometimes we get these prominences. I'm going to be talking about sunspots and why they burst and what happens when we do that. So we can get into more details of that in a second. But that's the overall structure. So just to quickly recap, we have the core. That's where this fusion is taking place. It's incredibly dense. It's about 15 million Kelvin there. Pressure is 200 billion times what it is on the surface of the Earth. Then the photons from this process, which we'll describe in a second, start to travel out, and that's what we call the radiative zone. And they're able to travel essentially from the center out, with a little bit of randomness. But once it reaches a little bit lower density, we reach this convection zone, and that's where the hot plasma here starts to rise to the top. It cools and it falls back down. So we get this layer of convection that happens because of the change in density further out. Then we get to the photosphere. This is the part that we see in the optical region, the visible light spectrum with a filter, so our eyes can see it. Then the chromosphere, that's the ultraviolet X-ray part of it. And then the corona is this bizarrely super hot region out here. Yeah, so I am going to be talking about that, Andy. Thank you. About radiation pressure. And in fact, that's what we're going to be getting into right now. So the nuclear fusion process that we have, you really need the correct environment for this fusion to happen. And it really is just because we're at this temperature of 15 million Kelvin. It's just a super hot, dense gas. Now, again, I said, too, fission is separating the nuclei. Fusion is bringing nuclei together. Fusion is what is happening in the sun. Now, oh, I got an alert. Oh, thank you. Thanks for the follow, Pangendrum. I appreciate it. The tricky part with fusion is it's actually incredibly difficult to occur. That's why we use fusion in nuclear reactors. I'm sorry, I do this all the time. That's why we use fission in nuclear reactors here on Earth. You split them apart. Fusion is where you bring them together. But when you bring them together, they have to overcome the electromagnetic forces. Remember when we talked about the electromagnetic forces back when we were discussing physics? It's the idea of magnetism. We have protons, two protons. Protons are going to repel each other. They're both positively charged, and positive sides of a magnet, they're not going to be able to meet. They're going to repel each other unless you get them so dense and so tightly packed that they overcome that, and then the strong force that holds protons and neutrons together takes over and overcomes that. That's when that fusion happens. But, even when I've described our solar system formation, I've been very blasé with the fact that, I just say, oh, yeah, we have hydrogen atoms, and then in the center it gets so hot and so dense that they get pushed together, and then we get helium. And then we get helium is actually fairly complicated. It's something called the proton-proton chain. And if you've taken astronomy before, this is one of those things that's probably gave you a little bit of an eye tick, and that's okay. Because it does for me too. This was really hard to remember for exams and stuff. But the proton-proton chain, we'll go through it step by step. So in order to get hydrogen to turn into helium, you first need to start with your hydrogen, which is a single proton. Now, two protons are pushed together close enough. Initially, they're repelling because of electromagnetism, but then they get hot and dense enough that they fuse and they make a deuterium nucleus. So that's one proton and one neutron, and it actually releases energy there. And so what's going on? Because you're like, okay, it was a proton and a proton. They come together. Now we have a proton and a neutron? Not two protons? Yeah. What happens is that this process converts a proton into a neutron, which takes down the charge to just +1. And the lost positive charge is carried off by a positron, which is the antimatter of an electron. It's an anti-electron. And a neutrino is also produced in this step. Now that positron, the anti-electron that made one of these protons turn into a neutron, we can just say it's this thing here, it does not live for very long. Once it runs into a normal electron, they obliterate each other and give off gamma radiation. Matter, antimatter, when it meets, it obliterates itself. There's a lot more electrons out there. So when a positron hits any electron, it's going to be obliterated. Bonkers. I agree. Okay, so this happens. Now we have a little bit of a soup of... Agreed, Cairo. Yes, deuterium and anti-deuterium are sometimes what they call out for being used in warp drives. But yes, that is typically what they refer to as the matter and antimatter that they use in warp drives. They have it's basically a solar reactor in your warp core. Fun fact. Okay, so now that we have our deuterium, we have lost our antiproton. We lost our antiproton. We lost a neutrino. And now we get into step 2. Now we have our deuterium, and it fuses. Again, it's still in this very it's still in this very hot area, that we have these loose protons around, that one of these deuterium nuclei collides and fuses with a proton. When that happens, now we end up with 2 protons that did not get converted and 1 neutron. The process of doing this, so this is helium-3, right? Helium in its standard state is 2 protons, 2 neutrons. It has an atomic mass of 4 and an atomic number of 2. So remember, the 2 protons is what makes it helium. The mass is what we call the isotopes. And we don't say it's an isotope if it's just helium-4 because that's its standard. But here it's helium-3 because there's only 1 neutral particle there. And then a gamma ray photon energy is released here that allows that to fuse and happen. So that's that energy lost when you overcome the electromagnetic force. That's that gamma ray being radiated off. And remember, that's the highest form of energy that we have. So gamma ray radiation, that's the puppy we want right there. That's the energy we want coming off of it. Now, once we have our helium-3 atoms, this is going to be adding another neutron to the process. Now, this can happen in a few different ways, but the most common way is through a collision of 2 helium-3 nuclei, as you can see here. That's why we've showed this in 2 chains. Because when you get this to happen and to come together, you get 2 protons and a neutron, 2 protons and a neutron. They fuse together, kick 2 of those protons off, which, guess what, are able to come back and be this free proton that makes the helium-3. What? Right? Bonkers. So that is where you're getting these free protons that are fusing with the deuterium that make the helium-3. The helium-3 comes together, and then we have now 2 protons, 2 neutrons, and we have a happy, stable particle that will live long and prosper. Okay. So that's the general process. That's what we call the proton-proton chain. And I've had to teach this as well as learn about it. I've learned about it twice. I've had to teach it. This is the 4th time, and every time I start to understand it a little bit better. A little bit more of it sinks in. So don't worry about memorizing it. The overall reaction that happens, if you just want to... I just covered the screen with my hand. That's not how streaming works. If you want to block all of this out, the overall process that happens is you have 4 protons, these guys, come together and form a helium atom. That's how I always describe it, right? You have a bunch of hydrogen coming together, fusing helium. When that happens, energy gets released. That energy that gets released is gamma rays, neutrinos, and positrons. Now, I didn't mention anything about this middle step of, getting converted to a neutron, binding with another proton, protons getting kicked off. All of those, that's in the details. The overall thing you need to walk away from this is that you have 4 protons fused together, makes 1 helium particle, along with gamma ray radiation, neutrino radiation, and positrons, short-lived positrons. And yes, exactly, Cairo. As far as we know, as far as any of us know and understand, that this process is how everything other than hydrogen started off. We have when we talk about the Big Bang and the process that happened there, there's an era called recombination, and that's where the protons and electrons first combined and made hydrogen atoms that they were able to come together shortly after the Big Bang. Because it was still hot and dense, and positive and negative, they attach to each other. That's where it's called the recombination, which is a dumb name because it's just it's the first combination. That's where hydrogen came from. And then when all of those hydrogen clouds are just kind of hanging out and going through their processes, they start to attract to each other, they start to get more and more dense, and then they merge and start forming heavier elements. So exactly. So the question from M. Chupon here, in here, the electrons are just sort of wandering around doing their own thing, right? They're not really connected to these atoms. To some extent, that's true. And it just has to do with how hot it is, where we talk about this incredibly hot part of the sun. We have because we have hydrogen, essentially, which is hydrogen is a proton and an electron. But because it's so hot, everything's vibrating around so fast that it's very easy to strip these things off from each other. So that's why they're very easily stripped off. And that's why that density, when they come together and fuse, that's where you're getting so much energy released, because they're overcoming that electromagnetic force and actually bonding. So yeah, we do have effectively some free electrons floating around, and that's why the antipositrons just obliterate themselves super fast in that process. So hope that made sense. I hope I didn't say anything wrong. It's still a little bit hard to wrap our brains around, and that's understandable. And yeah, I think that's the details. That's as far the details as we want to get into here. And I'm glad you like that, Rydell. I agree. I think it's pretty cool. So here's that gravitational equilibrium, and Andy was asking a little bit about this too. We have this solar thermostat, and it's a pretty impressive process that we have here, where we have this nuclear fusion that's going on in the core, and so it's giving off a lot of radiation. As it's giving off that radiation, it's starting to push out a little bit. And so we have this, I want to try to step through this properly. So let me see what I want to start with. Let's talk about it collapsing down, right? We have this equilibrium. Yeah, thank you, Cairo. That's the right way to say it. You don't have a tight association of electrons and atoms. It's because it's ionized plasma. That was the right way to say it. Thank you. So when you have this gravitational equilibrium, let's start on this side, I believe. As it collapses down on itself because it's hot, that causes the core temperature to rise a little bit, which increases the rate of fusion. When the rate of fusion increases, now we're having the thermal pressures overcoming the gravity, so now it's not collapsing down as much anymore, right? So it expands, and then it cools down, and fusion goes back to normal. As it's cooling down, let's say that it starts to cool down too much, the fusion starts to decrease. Now we have a slight decrease in the core temperature, which means it's not pushing out as much, so the gravity starts to collapse down and heat it back up again. I hope that makes sense. That's really the more detailed explanation for this gravitational equilibrium of the radiation pressure holding it up and then the gravity bringing it down. And if at any point the gravity starts to win, then that's going to increase the radiation to push it back out again. And as it starts to push back out, if it starts to push back out too much, then it will cool off in the middle and it'll start to collapse back down. So that's why we have this equilibrium that's going on. It's pretty cool, pretty impressive. Now, this is my favorite fact about fusion. The photon that's generated in the center takes technically hundreds of thousands of years to make it to the surface, which I love. And I have definitely encountered some of you and it's okay, when we ask, do you know how long it takes light from the sun to reach the earth? When I ask that question, the answer I'm looking for is really 8 minutes. But if you're being very cheeky, you'll say it's 100,000 years. Because you have to define what you mean by light from the sun reaching the earth. What I mean is 8 minutes from when it pops out, traveling at the speed of light to us. Great. What's really going on is the radiation that's being generated is happening at the core. And when it's happening at the core, now you have this little photon, this high energy gamma photon making its way out. Now it's running into stuff so it might not be even the same photon because that energy might be absorbed and then re-emitted. Remember, we have this absorption emission process that happens. It gets flung off in different directions. All of this sort of adventure happens. We call it it's a random walk. The technical term is really radiative diffusion, which just means that it starts to collide as it goes out, whether that be with one of these free electrons in the ionized plasma or whether it's absorbed and re-emitted. Yeah, exactly. That's great, Becca. Talking about, okay, do I measure from the center of my square or the corner? Yeah, exactly. That's the center. That's if you want to be a difficult DM. It's all in the details. So yeah, that's one of my favorite facts, that if you walk away with nothing else today, that's your Friday fact, that a photon basically takes a random walk from being generated from nuclear fusion, and it actually takes about 100,000 years, hundreds of thousands of years. We're in that different, order of magnitude before it makes its way out. And whodunit, redeemed hydrate. Oh, I still have some water. Thank you. Much appreciated. Okay. Thanks. Yeah, there you go. Measure from border control, absolutely. And P Frock, thank you for the follow. Okay, so we've done all this stuff. The next question you ask, especially like I find about 8 to 10-year-olds are going to ask, but how do we know that? And anyone can ask. You don't have to be 8 to 10 years old to ask that. But it's a good question because we get hung up on the science, and you need to take a step back and be like, wait a minute. How do we actually know this? And there's 3 primary ways that we can study the inside of the sun. Study the inside. Good, Sky. The first one is mathematical modeling. Now that we have computer capabilities that are actually able to sustain that many particles, do this sort of particle energy analysis. It was one of my first ever jobs as an undergraduate researcher, was to model a plasma. That's a typical thing. You put a bunch of different particles together with different properties, and you enter in the laws of physics, and you basically hit go, and you see what that process is, and then see if what you're able to observe based on your initial conditions is what you got out of that model. That is okay, Sky. That is good science training right there. Another thing that we know, which is pretty bonkers, is observations of solar vibrations. And that's the picture that we're showing there. Now, this is vibrations from the sun's surface that are measured using Doppler shifts. And I'm actually going to refer to the book because I know I can't explain it as well as they can explain it here. So these vibrations are what are resulting from the movement of gas within the sun, which generates waves of pressure that travel through the sun like sound waves moving through air. So, just to kind of rephrase that, we have movement of gas. Remember, we have this convection zone. We have this material that's in there, even when we're getting to the photosphere and the chromosphere. Those vibrations basically generate waves of pressure. If you think of sound waves, those are compression waves, similar to what's going on here. And then what we observe is these vibrations on the sun's surface by looking for Doppler shifts. So this is literally a measurement of Doppler shifts, where we can measure the spectrum coming towards us or moving away from us. Remember, we have that solar spectrum very carefully measured, where we have all of those peaks of what the composition of the sun is made out of. This isn't a picture taken with a camera. This is measuring every single pixel on the surface and figuring out how far that spectrum is actually Doppler shifted, which is crazy. I'm so sorry, Becca. The way that I help reconcile the Doppler shift thing in my mind is thinking of the slinky. So I always have my mind immediately be like, Doppler shift. Okay, slinky. We hold a slinky between us. You walk away from me, the slinky's going to stretch out. You walk toward me, the slinky's going to come together. If you think of that like these waves and this spectrum, that's the spectrum moving one direction or the other. If it's blue shifted, that means it's moving towards us, so it's moving slightly up the spectrum. And then if it's moving away from us, it's slightly red shifted, which is moving away from us. The way they colorized it here is that the lighter parts are moving toward us, the darker parts are moving away from us. And it's just measured by the peaks in the spectrum being slightly offset from this base standard. I hope that makes sense. And so you can see there's a rotation to the sun here. Yeah, there you go. I like that, Mammoth. That's awesome. If you tighten it, it's actually, yeah, that's cool. So what you can see here is actually the rotation of the sun as well. Like I said, this looks really pretty, but if you think, I always do this when I see this picture. I'm like, oh, okay, that's a cool picture of the sun. Then you go, wait a minute, because that picture looks like there's sunlight coming from this direction. And there's not. Sunlight comes from this whole thing. And what this actually is this side rotating toward us, this side moving away from us. That's the Doppler shift of the rotation. And then the individual Doppler shift that you see there, that's the different slight vibration patterns of the sun moving toward us and away from us. Crazy stuff. But this is a great way to compare the mathematical models that you build and you dictate what the sun is made out of, what processes are going on the inside, and how that affects the surface. Because it will affect the surface by showing up in these vibration patterns. And so if you have this from an observation, you can compare this to your internal mathematical model and see if you have a same external picture of the sun. So that's how we combine these two here. Quite similarly, we also use solar neutrinos. Neutrinos are weird, and I'm not going to spend a ton of time getting into them, but remember we talked about that proton-proton chain. Neutrinos were some of the components that were given off when we went from the free protons into deuterium. Good question. Okay, good question, Domestic. So the photon... Yeah, I'm going to pause here for a second. Question was, is it moving slower than the speed of light until it leaves the sun? And it's not. But that is a very good question. What's going on is it's going to travel at the speed of light, and then it's going to get thrown in another direction. And then it gets thrown in another direction, both from being absorbed and re-emitted from atoms, as well as just running into electrons. And similarly, a transfer of energy happens. So, now, yeah, technically the speed of light is lower, but not to the extent to actually slow it down to be 100,000 years to travel the radius of the sun. The primary mechanism that slows this down is not that it's being slowed down, but that it's getting thrown in different directions. So it's a random walk, as random as I can make it, for 100,000 years before it eventually makes its way out. And that's part of the mathematical modeling that they're able to see. So that's a really, really great question, though. I'm really glad you asked that. So thank you. And I hope that makes sense. I know it's a little counterintuitive to think about, but it's just there's so much stuff there for that photon to run into and interact with and get thrown in new directions. And it's really just a random walk that happens from that. So talking about neutrinos are subatomic particles that are very low interaction. It takes a lot of material for a neutrino to go through before it actually interacts with something. They're very, very tiny particles. They rarely interact with form of matter. They pass through everything. Got all of that. So this is a great analogy. An inch of lead will stop an X-ray. Now, an X-ray being a high-energy photon. An inch of lead will stop that. To stop a neutrino, your average neutrino would require a slab of lead a light year thick. Neutrinos barely interact with matter. They pass through us all the time. So neutrinos that are produced in that proton-proton chain, when we go from protons to deuterium. Did I say that right? I think I said that right. Yes, deuterium. The neutrinos that are produced then, they pass through the sun as if it's not there. They'll just there you go, same density. I like that. They're formed in this proton-proton chain. The neutrinos just zip right out of there. They're not going to interact with anything to slow it down. So they travel pretty much as if there's nothing there. They reach us in effectively minutes, which gives us a way to monitor what's going on in the center of the sun. Oh, Christoph. And yeah, neutrino detectors are pretty bonkers. So that's the reason we want to detect them, though, because if we're able to actually detect them, then we have a much closer to real-time monitoring of what's going on in the center of the sun if we can detect the solar neutrinos. So they do occasionally interact with matter. You are able to capture a few solar neutrinos with a large enough detector. They're very partially successful. The early attempts to detect solar neutrinos captured only about 1/3 of what was predicted by the models for the sun, and it became known as the solar neutrino problem. And this actually was for about 3 decades. When we first started detecting neutrinos, we were like, yay, we can measure neutrinos from the center of the sun. We're starting to detect them. Oh crap, there's only 1/3 of what we expect. What's wrong? Like, who's in the wrong? Is it our observation or is it our models? And so for a while, there was a lot of work going into trying to figure that out. Just be, agnostic, say, okay, something isn't matching up. We got to figure out what that is. And then they basically, this is actually really cool. So the missing solar neutrinos were going undetected. It wasn't that the models were necessarily wrong, but neutrinos come in 3 different types. 3 different types. We were only detecting 1/3 of those. So those 3 types are electron neutrinos, muon neutrinos, and tau neutrinos. The fusion reactions in the sun were only producing electron neutrinos, and the early solar neutrino detectors could only detect those. Once we got other neutrino detectors, they were able to detect all 3, and they confirmed what the amount should be. So, in other words, the electron neutrinos produced by fusion change into neutrinos of the other 2 types during their transfer out of the sun. And that was the most fundamental breakthrough that they realized with that. Now, how they do that, why? Because that's a whole other class into subatomic physics that I think is a little bit more in the weeds than we need to worry about now. But the cool fact and the fun thing we want to take away from that was realizing that those neutrinos are basically changing their form as they're coming out. So even though it was only producing electron neutrinos in that one fusion process, that's what they were building the detectors to measure. They were only seeing 1/3 of them because all of those the 2/3 originally were electron neutrinos, but then they transferred into other types as they were leaving the sun. And yeah, so Todd brought up there's the Sudbury Neutrino Observatory in Canada. It's 2 kilometers underground and is insane to visit. Once I'm done here, which is in about 10 minutes or something, look up neutrino observatories. They're so cool. They're essentially like tanks of water. The Sudbury one, I think, is this like massive sphere that's underground. They're really, really cool. Really fascinating. And I believe there was an earthquake in Japan like obliterated one of their neutrino detectors. But fascinating stuff. So that's how we know what's on the inside of the sun. Now let's talk briefly about sunspots and magnetic fields, and we're definitely going to take the full hour because we just got really excited talking about the sun. So we looked at that rotation that was going on with hey, Talia. So we looked at the rotation from the sun there in this image. We can see it rotating here. Yeah. Oh, Cairo pulling out the DS9 knowledge. All right. Yes, Seth, that's a great one too. Saw an interesting one where there was an underground half dome that light up when neutrinos pass through it. No worries, Smokestack. Happy to have you here. Okay, so the sunspots that are going on we see these sunspots on the surface of the sun. How do they form? They form because we have this big ball of plasma that's rotating. But as it rotates, it's not a solid brick. It's not a solid object. It's a plasma. And so we have differential rotation. It's actually rotating faster on the outside to try to keep up than it is further toward the top. When it does that, that plasma in the magnetic field does start to stretch, and it starts to essentially get out of whack a little bit and form these sunspots. Oh, who done it? Thank you. Hi. So these sunspots are formed. Remember, we had this convection layer that was going on. Oh, Lake Girl, thank you. Carrick Jazz Hands. This is where the rotation of the sun and that plasma starts to develop those sunspots, because we have this convection layer where we get this rotating plasma that's being convected, and then also the differential lateral rotation as the sun is spinning around. It starts to, the magnetic fields that are being twisted up start to suppress the convection and stop that surrounding plasma from sliding into the sunspots. So then we get this magnetic field that essentially pops out here, and these sunspots, which are slightly cooler than the photosphere around them. So some of you may have seen pictures of sunspots like we have here. They're these dark spots that are observed on the photosphere. And even if you just use a box camera or some way, or solar filter, anything, just in the optics, that's the photosphere, you can see these dark spots. Now, if you're to look at it from the corona perspective, you can see the prominences that are coming off of it, and that's that magnetic field. That's all this gas that we're getting in the corona, those charged particles, they get trapped in those magnetic fields, and you can see it pair up these sunspots here. Now, sunspots come in cycles. You may have heard about this, sunspot cycles. And they essentially come in cycles because of this process where the sun is rotating, this plasma ball is rotating. We have differential rotation. As the equator is rotating faster than the poles, that magnetic field is starting to spin. The overall magnetic field is starting to spin up, but that spin up of that affects the convection layer, gives you these big churns here. And then the way I like to think about it is those magnetic fields, because it's continuing to have differential rotation, are getting twisted up like a rubber band. You get this, if you took a rubber band and you just twisted it and twisted it and twisted it, it would get tighter and tighter and tighter, and eventually it snaps. And when it snaps, we get solar flares, the sunspots go away, and the sun basically goes back to more of an equilibrium, and then the process starts all over again. So those magnetic fields get all twisted up, and then they all snap, and then they go back down. So that's how we have these cycles of about 11 years. And you can see the black line is observed them, the red line is predicted sunspot cycles, and then this is a little out of date, but a prediction that we have there. And this just comes from, again, our mathematical models, observing the sun, understanding what the plasma is. It's not perfect, but it's a way to think about this 11-year cycle that we see with sunspots. And so because of that, now this is the corona that we're looking at. So this is, remember, that X-ray, ultraviolet radiation. This is where we're able to actually see what the magnetic field lines look like in a high solar activity region, particularly here. Now, if we were looking at this in the optics, we would just see these as dark spots. We're not seeing them as pairs, but it is essentially magnetic field pairs that we have right here. And that is the rubber band that's building up and eventually snaps and gives us solar flares. And in the worst case scenario, we get something called coronal mass ejections. When that snap happens, sometimes it's close to your face. The best way I can phrase it. And not just radiation, but that's a bunch. Remember, those are all magnetic particles. These are sort of massive particles, charged particles, hot particles get flung out. And that's what we call a coronal mass ejection, or a CME. And these can be very, very bad. This is observed with one of our solar telescopes that we've used back in 2000. We observed a coronal mass ejection that happened here. That's the sun. We're covering the sun so we can actually see the whole thing there. And you can see this massive ejection. I mean, that's many times the size of the Earth that's coming off of the sun here. I agree, Cairo. There's lots of great material for that. So I can't not bring up solar flares and CMEs without talking about the Carrington event. Now, the Carrington event, the only sort of picture we have from this is it's named after the solar astronomer Carrington, who had been taking very detailed maps of sunspots. And this is his map of the surface of the sun around the time of the Carrington event that happened. But what happened was a solar flare, a CME. So basically, a solar flare is a lesser version of a CME, I guess, is a way to phrase that. You're still getting these bursts. You're still getting a release of energy, but you're not getting like a ton of plasma material that's coming off of it. It's more just a flare. If you think of this, like more this stuff down here that's coming off of the corona, and can sometimes be a burst, a quick solar flare. But this is like a bomb going off. A coronal mass ejection. And so what happened in 1859, a coronal mass ejection hit the Earth, and it was big, and it was bad, and it was just at the beginning of the Industrial Revolution. I guess in the midst of the Industrial Revolution. We had telegraphs at the time. The big sort of anecdote from when the Carrington event happened is that it destroyed any transformers that were built. We got this huge surge of plasma that hit our atmosphere. All these charged particles hit our atmosphere and just obliterated all of the electricity that we had set up. So it caused transformers to short out. The telegraph system like completely went down, but in a weird way. The telegraphs actually... Oh God, something just scared the crap out of me. I don't know what it was. The telegraph system actually... It went down, but before it went down, people who were working the telegraph actually got sparked. Like arcs flew off of the telegraph. Telegraph paper caught on fire, and then when they unplugged everything, they were able to still work because there was just so much static electricity in the air. So it was pretty crazy. Yeah, all of the bad things happened, and it was a lot of recovery from that. And Carrington was able to kind of associate that with the solar activity on the sun. Now, Cairo asked the question, do we know if we've had any CMEs since then that caused actual destruction on Earth? Not that level, but we had a very close call. This is from 2012, hilariously enough. This is Earth. This is our rotating sun. We missed this event, that thing, by about 9 days. They did not, peace themish, and if they did, even that couldn't really hold up against it. Thank you, Dr. Derp. I appreciate that. I don't know what it is yet, but I'm sure it'll be an adventure. But seriously, we missed this event by about 9 days, and this is Carrington level destruction that came off of the sun. If this had hit us now with our technology, now when I was first teaching this, probably in about 2014, I said we'd probably still be crawling out of it. Okay, so thank you, Becca. This is a compilation of data from various solar telescopes. We are looking top down on the sun. So this isn't that we have a telescope that is above us looking down. This is a compilation of data. You can see these different telescopes are all out here. They're measuring this information and then building up, because you have these lines of data, and then building up where all of those are being hit. And with our knowledge of the rotation of the sun. And so because Stereo A got it in the face, we have a lot of data from that, and we were able to kind of see what happened from there, as well as the other angles from these other solar telescopes. So yeah, thank you for that clarification. But this hit in 2012, yeah, missed us by about a week. And I would say by now we'd be crawling out. of it, but I think our satellites would be gone, internet would be gone, cell towers would be gone, transformers would be gone. We have very little ability to protect against something that massive. We do have protection from solar flares. Monitoring solar activity is a component of doing satellite, maintenance, that sometimes you will lose your satellites, and you monitor the solar activity for that to make sure that. And yeah, M-Chupon, so we could mitigate a lot if you unhook the power grid before it hits. And there are some mitigations that I think different governments have tried to take. I would say, so you could say we have 24 to 48 hours of warning. In theory, you can look back and say, okay, we saw indications that this was going to hit 24 to 48 hours early, but it's hard to know when that's actually going to happen and when it's not. But I think you do start to get a surge, particularly of X-ray and gamma radiation beforehand. We also have these telescopes, monitored out, and now we have telescopes that are much closer to the sun. Problem is that they communicate as well. So the high energy particles will still hit us, but the plasma is going to be taking a little bit longer to travel, and so you've got to be able to turn it off. Yeah, it would fry. So anyway, it's just apocalyptic and fun and still something that we have to worry about. But if you want to think about ways that space could take us down, this is one of them. So Stereo A survived this because it was designed to survive things like this. But it definitely, it did blow out some of its pixels, and they had to calibrate beyond that. As well. Yeah, right. Exactly. So on that note, it's Friday afternoon. Next week, we're going to be talking about different types of stars out there. We'll be discussing the Hertzsprung-Russell diagram, which is one of my favorite things and a key component of learning astronomy. So I encourage you all to make it for that. And if you missed this or you're watching it after the fact on YouTube, you feel free to join us. And you can find the link to the YouTube down below or the Twitch channel, depending on which platform you're watching this on. And I want to thank all of you for hanging out and asking excellent questions. We went over the time. Our class took the entire hour this time. So, yeah. So I appreciate all of the fun engagement and all the support. And we will be back. I will be back. Oh, Trivial Prosciutto, thank you. I will be back on Sunday with our Star Trek brunch, but I do have an event tomorrow that will not be on my Twitch, but if anyone is interested, I will be interviewing our good friend Mohammed Noor, who's a biology professor at Duke, at the Fort Collins Book Festival, and those times are Mountain Time. So you can find it on that website that I just posted in the chat, or on their Facebook page, but the Fort Collins Book Festival. So, excellent. All right. Let me see if there's anyone up we can go say hi to. Looks like Physics O is teaching. Let's go say hi to them. All right. Well, thank you all very much again for hanging out. Take care of yourselves and each other. Stand up, stretch, do all that fun stuff. And I look forward to catching you next time. All right. Thank you, everyone. Bye. Tell them I say hi.